So, good morning everybody. Welcome to this last session. Before beginning, I just wanted to make a quick announcement. So we have today some little changes comparing to the initial program. So Ralf will start speaking during something like half an hour, I guess. Then Nick will give his lecture, and we'll have a break. We'll break for something like 20 minutes, and we'll try to make a picture of everybody. Yes, unfortunately you won't be there, but anyway. And then we will have the second lecture of Nick, and the end session will be simply answered.
So, good morning. Can you all hear me? It was quite challenging to get up this morning. So usually liquids also have some chemical components that, affect the metabolism. Anyway, this is where we stopped yesterday. We talked about the turbulent initial conditions, the collapse and the interaction of prestellar cores and dense clusters, and the thermodynamic properties. All of those processes affecting the formation of stars, affecting the IMF, but also many other features. The one big topic that was missing is the discussion of stellar feedback. And as you will see, this is, I think, the most uncertain area in star formation theory, because there are many ways of achieving feedback. There could be ionizing radiation, there could be outflows, there could be winds, there could be supernova. But in principle, if you talk about galactic scales, we also need to speak about chemical feedback, the chemical yields that can drive the different chemistry, the metallistic gradients that we observe on galactic scales. So usually when we speak about feedback, we are thinking in terms of high mass star formation. As you know, the luminosity of a star is a very strong function of the stellar mass. It goes with the 3-point-something power. So if you double the stellar mass, you, tenfold the luminosity. And it's not just the luminosity, probably all other feedback processes scale non-linearly with the mass of the star. So the question is, how do high mass stars form? Because there is a conundrum in high mass star formation. What you can do is you can look at the luminosity that a, let's say, 10, 15, 20, 30, etc. solar mass star puts out. And you will see that if you do one-dimensional calculations, there's a limit where radiation pressure exceeds the typical accretion rates. So the radiation finds a dust grain or an electron or whatever, it interacts with it, gets absorbed or scattered, and there is a momentum exchange. So there is an outward pressure, an outward force that is due to radiation or winds, and it can balance the inward force, the gravitational acceleration that the particles have due to the gravitational attraction of the central star. So there's a big conundrum in massive star formation. How the hell can you form a massive star if at 10 or 15 solar masses, the luminosity of the star should be enough to blow away the ambient gas cloud? And as always, we realize that these one-dimensional considerations are too short, and we need to go to higher dimensions to solve the problem. So the idea is indeed that you have an accretion disk around the star where the material is much denser, and the radiation, the wind, or whatever feedback process you would like to have escapes along the polar axis, where usually you have a much less dense gas, and radiation and winds can escape more easily. So just from going from one dimensions to 2 dimensions and then to 3 dimensions, you see that the accretion in the mass growth history changes dramatically. So this is why high mass star formation inevitably needs to consider thoughts about feedback processes. So the questions here is, how do massive stars form in the associated cluster? How does this massive star formation then modify the subsequent star formation? How do the massive stars influence then the formation of the small guys around? What determines the upper stellar limit? If you look here at the IMF, we see there's hardly any star above 100 solar masses. And most of the, 200-300 solar mass stars that have been discussed in the past have been shown to break into a very tight binary, triple, or whatever system. So if you think of it, you have between the mass of a proton and the mass of the galaxy an enormous range of possibilities. And yet, stars do only form within a mass range of, let's say, 100th to 100 solar masses. Only 4 orders of magnitude. And the question is why? So on the lower mass end, it probably has to do with stability, with the fact that you need a minimum mass to excite hydrogen burning in the center so that you reach a proper stellar phase. But on the upper end, this is much less clear. And I personally think it has to do with internal stability processes. Massive stars are very close to the critical limit that a polytrope can have. So a polytrope with 4/3 is at the critical stability limit. We can model these stars in quite reasonable approximation as polytropes. And they're radiation dominated, and we know the equation of state of radiation dominated material has 5/3. Or as Nick would say, the effective equation of state. Good, so how do you model that? And I should say I do not address the question of outflow feedback, because I personally think it is not so important compared to, well, to ionizing feedback or radiative feedback. But again, if you ask different people, you get different opinions. So this is from a calculation that Dale and Bonnell just recently published. It is a cluster-forming cloud, and it has a few high-mass stars, and these high-mass stars do shine UV light. They have developed some ray tracing scheme that works with this SPH simulation. So basically you shoot rays and you kind of find yourself a pathway along the nearest SPH particles. It works nicely, but it has also certain drawbacks. And this is then the coldish gas, and this is a more ionized gas. And you can see that it influences the star formation region. It blows an H1 bubble. However, if you look closely, you see still filaments of cold gas bringing fresh material towards the center, and star formation is not stopped in such a dense environment. So I think one of the outcomes of these type of calculations is if you have a very dense cloud, it is extremely difficult for radiative feedback to actually do something, because it always finds channels of weakest resistance, of low density, where then the effects of radiation or radiation itself can escape, and radiation pressure. So you need to go to very low density environment to see really an effect of radiation pressure. And again, this is debated, and one probably can argue that this cloud they put in here was quite in the high density regime, and most clouds would be of lower density, and hence would be more affected by radiative feedback. So what they did is here, they looked at the parts of the gas that is affected by the radiation, and you see for some of the sources, they kind of, if you look on their sky, so basically you sit on the source and you're looking where does my radiation go and where is it absorbed, then you see some affect quite a region around them, radius of 5 parsec, and others, only have very small regions where they do effectively something. So here radiation feedback would not be so efficient. This is from a recent simulation by Mark Krumholz. Again, excuse me, a similar question. The typical spherical blob of gas, you shake it with some turbulence, you let high mass stars evolve, and you look at what comes out of it. And here the radiation transfer is solved more with a diffusion scheme. You can do that for different cloud properties, a bit more turbulent, a bit less turbulent. I think that was a bit more turbulent. You can do that with outflows, and you can then look at the mass accretion rates, if you wish. This is the time in time scales of the total freefall time, well, scaled to the total freefall time. And this is the number or the fraction of the mass accumulated in zinc particles, in stellar particles, with respect to the total. So here 20%, 40%. And you see a slight difference between feedback and non-feedback, but altogether feedback cannot stop in these conditions the accretion. So what you can do is you can zoom into smaller and smaller scales. So this is not a cluster forming simulation, but this is a bit older work from Krumholz, where he takes a small blob of gas and looks at how the gas accretes onto the central object. And again, you should keep in mind that this was with a very centrally concentrated initial density profile, and I will show you soon the results of a calculation that has something that looks like a Bonner-Ewert sphere as initial condition. So the conclusion here is, if you go to 2D or even 3 dimensions, radiative feedback, here modeled as radiation pressure, does not stop the accretion. There will always be cold and dense flows that find their way towards the center. Now, as a point of caveat, these calculations have been done in the past in 2 dimensions. So this is work by Hal York and Cordula Sonnhalter in 2002, where they took Hal York's 2-dimensional radiative transfer code, exquisite physics, lots of detail in, but 2 dimensions. And because the disk has no possibility to become gravitationally unstable, what you see is that the intense UV radiation that is put out by the central star is able to burn a hole into this disk. There will be no spiral arms, no channels of gas, of dense gas reaching the center, and this stops accretion. So this is another example where you find a different result, a really qualitatively different result if you change the dimensionality of your problem. And that is a typical feature of these feedback calculations, that if you treat the dimensionality of the problem not correctly, then you may get it wrong. So I show you now stuff that we have done, simply because I know it best. It's, again, a very simple numerical approach. We take a 1,000 solar mass blob of gas that suddenly comes out of nowhere. It has a Bonner-Ewert density profile. We give it a small m equals 1 perturbation with a very small fluctuation. It is unstable. It has a big zinc particle, but the actual zinc particle radius is smaller in the other calculations. And it has cell sizes of roughly that size. So it uses flash. It uses a protostellar evolutionary code or model that runs inside the zinc particle to tell Thomas Peters what the feedback is looking like, how much UV radiation, but also heating radiation he needs to put out. There's a rate equation for the ionization, and most of the relevant heating and cooling processes are included, and you can, because it's a grid-based code, you can put in magnetic fields and other things. So how does it look like? Box size is 0.3 parsec, disk edge on, disk face on, and you see that the massive star starts to blow a hot ionized bubble. And because there are more, you see a bubble here, a bubble there. And this is by no means symmetric. And this guy managed, it gets shot out, actually down. So you see it is a 3-dimensional problem. Accretion flow comes sometimes from the top, sometimes they come from the bottom. And that is important for observations of H2 regions, for ultra-compact H2 regions, because there is a conundrum evolved in looking at ultra-compact H2 regions. There are too many. If they were just ever expanding on a constant rate into a homogeneous density background, there should be much, much fewer ultra-compact H2 regions. And we should see more massive and extended H2 regions. You can do that with a magnetic field. And I show that because it is one of the most successful rendering attempts we have made. This is the density, this is the pressure, and you see that the structure of the outflow that develops looks very different to what I've shown you before. Before, these outflows were kind of patchy and fluctuating, strange, and now they're more spherical. So the presence of ionization, more the presence of complex structure and instabilities in the accretion disk lead to a change of the outflow behavior, of the magnetic outflow behavior. This is why you find spherical outflow cavity and not an elongated polar one. I can't back to that. We can look at the interplay of ionization in the magnetic field. So this cavity is created because it's a magnetic bubble. So what happens in these magnetic tower flows, here you have your disk. The disk is threaded by magnetic fields, but the disk is wound up. No, the magnetic field is wound up by the circular motion in the disk. So you build up a very strong toroidal field, you build up magnetic pressure, and it releases its tension by trying to straighten out the field lines, so the field lines detach and lift more. They're still anchored in the disk, but they try to expand, like a spring, right? So they start to lift off, they drag along material. There's also the centrifugal way of accelerating material along these field lines. So what you drive usually is a very polar-like outflow. Do I have yes, here I have a picture. So this is what you would get with a weak magnetic field. Now, if you have a strong magnetic field, then it's much more difficult to create these outflows, and they have a different shape. And what we see here is also, and the question is why does it correlate so well with the magnetic field? You see also that the disk has different parameters and it gets unstable. So in order to wind up the field lines, you must have good coherent rotational velocities in the disk. Now, if you have fragmentation, if you have the interaction of spiral arms, if you have complex motions due to protostars cruising around at random trajectories, then you are no longer sustaining a coherent field structure in the inner parts of the disk. So your outflow launching radius moves to larger and larger scales in the disk. So if you go back here, initially you would drive the outflow here and then here, but because here you are getting rid of the outflow strength because you have fragmentation, the launching radius moves further out. This creates these more spherical bubbles. And this is correlated, this is correlated with the field strength, also with the field morphology in a more complex way, and I will not discuss that. The other thing to notice is that basically this cavity is driven by magnetic field. So the energy is dominated by the energy density in the magnetic field, so B squared over 8 pi. However, if you have the ionized region, and again it's not spherical symmetric, there's an accretion flow from the top, so ionization can only break out at the bottom. If you look at that, the magnetic field is pushed out. So the magnetic energy density, or the magnetic pressure, is very small, while the thermal pressure here is very large. So it is the thermal pressure because the gas is very hot now, it expands, pushes away the field lines, but if we were to overlay the two images, you would see that there's hardly any pressure change. So they are in pressure equilibrium between thermal and magnetic energy, which is in principle expected in the hindsight, but it was not clear at the start of the simulation that you get this beautiful balance and that the H2 region does not really affect that much the magnetic tower flow. Good. Now, the question is, how do we form the massive star? So this was an initial condition that was chosen to do anything right such that the central object gets most of the mass. So there was no turbulence, it was initially homogeneous, it had a certain rotation, it had an m equals 2 perturbation, so all these things people typically do to get most of the mass towards the central object. However, it turns out that it's actually very difficult. So why is that? What is plotted here is the density, the temperature, and the stability parameter of the disk. And it turns out that the disk is, now we use a local Q parameter that is of course a very fishy definition because Q knows about the radial instability in a one-dimensional axial symmetric disk, thin disk, but nevertheless it gives you some educated guess about the dynamical properties in this disk. So what I plot here is the mass in several components as function of time, 0.6 mega years to 0.68 mega years. So only, what is it, 8,000 years in this evolution. And this is the total mass in the disk and central and stars. This is the mass in stars, and this is the mass in disks. So you notice that the mass in the disk grows. The mass load onto this disk is larger than its capability to transport material inwards. We had that yesterday. Then it becomes unstable. But it remains in this unstable mode, so it maintains roughly always equal masses. Disks tend to be self-regulating. If they have a more stronger, more heavy mass load, they get slightly more unstable, they form more stars, and get rid of this excess mass. So there seems to be an upper limit of the mass such a disk can sustain. And this excess mass goes then into stars, right? So if you put the, what is it, red and the gray one together, you get the black one. That's interesting. You can also see then where the particles form. So star formation starts, of course, in the very center, but then the unstable regions move to larger and larger and larger radii, so new stars are formed at larger and larger radii. And again, notice that this is a situation where the disk is as stable as it can get because there was no external turbulence. These are different calculations with different feedback properties. There was a burst of star formation, so there is some excursion, but otherwise the trend is, there is a trend. Good. We can look at the mass accretion rates of the individual objects, or masses. This is a run without turbulence. This is a run without feedback where we suppress, differently. This is a run where we suppress disk fragmentation. This is the run where we allow for disk fragmentation. And the blue guys are then the mass histories of the individual objects that form. There are two things to notice here. If you suppress fragmentation in the disk, the overall mass accretion rate is slightly smaller. Why is that? Well, that has to do with that fact here. The instability moves further and further out. So material that drift through the disk towards the center finds new stars from which it can be accreted at larger radii, so it gets accreted earlier. It does not have to go all the way to the center to be accreted. So altogether this leads to a higher accretion rate because more or less the accretion sites move to where the gas sits. It's like the profit in the mountain issue, right? In this case, the profit goes to the mountain. Then you can ask, what happens if you have feedback? These are these cases here. This is suppressed fragmentation with feedback. This is not suppressed fragmentation. Feedback kicks in roughly here. And you see that if you put on feedback, it does indeed decrease a bit the accretion rate, but you cannot stop it completely. So stars still accrete, but at a slightly smaller rate, and this is the comparison run where fragmentation is not suppressed and no feedback. So 3 comparison runs. I show only 2 runs here, 3 runs here. Good. I skipped that. Well, this is almost the same here. We have magnetic fields, and the magnetic fields do reduce the degree of fragmentation. They make the overall evolution slower, but they do not suppress fragmentation and mass accretion rate. So then what limits the mass of the stars? If you look at these curves here, you know, none of these is ever increasing, right? Only if you suppress fragmentation and you have no feedback, then the mass of the central object would be ever increasing until we run out of the reservoir. But we have 1,000 solar masses, we stop much earlier. So why is it then that all these curves bend over? And the reason is a process that we call fragmentation-induced starvation, and it is in a sense similar to the competitive accretion. So if you look back 10 years, maybe 12 years, what is the idea of competitive accretion? The idea is you have a gas reservoir and you sprinkle in seeds, protostars at the opacity limit, all with the same mass, and then you see which one accretes faster. And if you recall your Bondi-Hoyle accretion, it is sensitive to the mass, to the square. So if you have slight fluctuations, maybe some guys accrete a bit faster, they then in the next time step will accrete even faster, and you soon have a runaway process, and you can build up a mass spectrum of objects. Now, this is not in this original competitive accretion picture how stars form. Stars form in blobs of gas with different densities and different masses that have been pre-structured by turbulence and selected by gravity to go into collapse. So it is not that you put in seeds in something that is homogeneous and they compete all together. They have their initial environment, and they first eat their environment, and then they look what's out there. Then, of course, the more massive guys, because they form or move to the center of the cluster, have a higher chance to sustain a higher accretion. So this is what I told you yesterday. But you can turn the story around. You can ask, let's assume we are in a situation where we suppress fragmentation. We only form one object in the very center, and this guy eventually gets all the mass. Eventually, gravity overcomes all the other processes, and the mass eventually ends up at the star, and it can sustain a high mass accretion rate for a long time. Now, assume, as we did, you switch off the artificial suppression of fragmentation. So the disk becomes unstable, it fragments. So not only do you have a central star, you have a primary star, you have a tertiary star, a quaternary, etc., and these guys sit at larger radii. And recall, a disk accretion lives by exchanging angular momentum, and then the guys can drift inwards. So there is a net drift through this disk towards the center. This feeds in the classic model of accretion disk, the central star. Now, if you have a binary star and you have unequal mass binaries, the people who do low mass binaries knew that for a long time. The more massive one sits in the center, the other one cruises around. Now, this guy who cruises around sits at larger radii, and as the gas drifts through the disk, it encounters the lower mass guy first, right? It's the one that is encountered first. It can accrete this material because the angular momentum fits. They move along the same trajectories, and then whoop, it gets swallowed by the secondary. So this evolution drives an unequal mass binary into an equal mass binary. And the same can happen here. So in these disks that are calculated here, you have fragments or protostars that form at larger and larger and larger radii, and eventually these guys that form later and further out get most of the mass that slowly drifts through the disk. So the one that sits at the largest radii gets his share, then the second one gets his share, and by the time the central guy wants something, there's hardly anything left. So the fact that you have fragmentation prevents the middle guy from growing ad infinitum. So fragmentation leads to his starvation. So this is what we call fragmentation-induced derivation, and I made an angular momentum argument. And you could say, well, but in a complex turbulent cluster, do you still see the same thing? Shouldn't there be always channels of gas that kind of sneak around these further outlying guys and deliver mass to the central star? Yes, that is correct to some degree, but when we look at the mass, so what we can do in such a situation, that is work by Girichidis et al., we can look at shells around the central star and look simply at the mass flow through these shells. And we can see that this mass flow diminishes as we go in and in and in and in, because the stuff, the protostars that lie at larger radii, eat away some of this mass. So even in a more complex turbulent environment, there are some things of this fragmentation-induced derivation left over. Now you can ask, what is this all about? Why do some guys say, oh, this is competitive accretion? The others say this is fragmentation-induced derivation. In the end, I think now we're talking about the same thing. So when people now talk about competitive accretion, they have changed, in some sense, the meaning of the term. So it is now acknowledged that the stars form self-consistently out of their immediate environment, that if they sit in the center, they have a larger reach because they get material from outside. But one should also say that they get less material than if the other stars would not be there. So in principle, these are the same thing. We are modeling the same physics. We just address different aspects of the same problem. So you should keep in mind that if there is some confusion about these two, how shall I say, terms, in the end, the underlying physics is very much the same. It depends on what your history is, how you call these processes. Good. Now, coming back to the ultra-compact H2 regions. There's a conundrum that, again, if you count ultra-compact H2 regions, then there should be very few. Because in the classical image where you have a protostar, massive protostar that sits, let's say, in a more or less homogeneous environment and accretes on a constant rate, the H2 region should be ever expanding, because the mass gets, the star gets more massive, gets considerably more luminous, so it can drive a larger and larger and larger H2 region. If you do, in a very crude way, the accounting, the statistics, you see that there should be much, much, much fewer ultra-compact H2 regions. They should all have been expanded into larger phases than what you see. And I think the answer lies, and Eric Keto has pointed it out a long time ago, that accretion can actually quench the H2 region. If you have accretion flows that are not spherical, not symmetric, and not steady, but have time fluctuations, maybe sometimes they come from above, then the H2 region sneaks out at the bottom and is quenched at the top. Maybe the accretion comes then a few thousand years later, more from the bottom. It quenches the H2 region there, and maybe radiation can break out at the top. You see that there is now no longer a one-to-one correlation between the age of the star and the size of the accretion rate. The H2 regions can flicker. They can go from an off to an on state and back to an off state again. And each time they start again, they start at ultra-compact H2 regions. And that explains why over the lifetime, the accretion time of a massive star, the fact that probably the accretion is fluctuating in time and is spatially structured, you can have these flickering accretion H2 regions. And indeed, we see H2 regions that are shrinking. A certain fraction of the observed H2 regions, of the ultra-compact H2 regions, is decreasing in flux. There is a study by Chris Dupré, who looked at, I forgot the house number, somewhere in the galactic center 15 years ago, and he's doing it right now. And he sees out of the 50 ultra-compact H2 regions that are in this region that about 3 to 4 seem to be decreasing in flux. We talk about timescales of 10, 15 years. And flux decreases of order of a few percent. So you can actually measure evolution here on these scales. So how do the H2 regions look like? This is the same, but now you put it in a radiative transfer post-processing. We have seen the code with which this has been done yesterday. And you can look at what the VLA would be picking up in terms of emission from these regions. And you see it flickers a lot, and it can have all kinds of shapes. The people who do H2 regions, as always in astronomy, classify them. So cometary shape, core halo, shell-like, well, irregular and unresolved. Wood and Churchwell, Dupré, etc., etc. And, you know, here it is. And this is the same region. It's the same H2 region. It morphs with time. It can be cometary, it can be shell-like, it can be quenched, can start again as a point-like one. It also depends on the viewing angle. So this is the same region. Now it's kind of cometary-like. Here it's shell-like. And again, these are not spherical blobs of gas. They can have very complex morphologies. And you can do the statistics, how many cometary, how many point-like, etc. You see, and it seems to fit, and it does not fit when you suppress fragmentation. So you need this complex interaction of the gas, the more complex flow patterns. This is just the flux that we see, and you see there is a decrease, then it jumps up again. So this you can measure. These are time scales of, oh, I don't really can count, of kilo years. Yeah, this is of order of 100 years here. So it can change on order of decades, let's say. Good. So I think many of these studies on radiative feedback indicate that feedback has a difficult time to suppress fragmentation at all and to stop the accretion onto stars. I think people agree that the accretion onto massive stars is not stopped by radiative feedback. Most people would subscribe to that. How strong fragmentation is suppressed depends probably on the code you're using, and it depends on which scales you're looking at. Very close to the massive star, where radiative diffusion processes are important and you're in the optically thick limit, probably indeed fragmentation is suppressed, but these disks can have 20,000 AUs or more. You observe them. Ralf has a beautiful example, for instance. And there could be fragmentation further out. And we know that massive stars form in multiple systems. We know they form typically in the centers of larger clusters. So fragmentation must occur. Magnetic fields can change the picture, but I would say not dramatically. Again, there's a debate depending on who you talk to. I think maybe a factor of 2 they can suppress fragmentation, but I would say not much more. The fact that you have these complex three-dimensional flows solves the problem of the large number of ultra-compact H2 regions. So more needs to be done because one needs to derive more observational constraints. If you want to do VLBA studies, for instance, then you're looking at radio recombination lines, so you want to do detailed radiative transfer of these things. Good. Now, I think I skip the questions of magnetic field amplification and go straight to the end. Let's see that I can manage doing this. And I would like to end by showing you this again. Yes. Yeah, there is a white bearded man up there who has an infinite computer, so to say. this is it. This is what we need to explain. And I think you have all the features, all the complexity that star formation and ISM dynamic has on this picture. You have the cluster, you have the ionizing bubble, you have the dust, you have the shocks, you have the winds, you have complex features. If you zoom into this region, you have young stars forming, driving outflows into the medium. You have magnetic fields that structure the region. So a very high degree of complexity. And I think if you look at this image, you realize a simple one-dimensional model that has, let's say, gravity and pressure, gravity and magnetic field is bound to fail. And only in certain peculiar cases, isolated low masses somewhere in nowhere, then these models may work. But on ISM scales, on cluster scales, we are faced with a complexity that I think only now we appreciate and understand. So what we need is we need a multi-scale and multi-physics approach. This approach at least, and this is certainly an incomplete list, needs to include self-gravity if we are wanting to explain something like that. Then we have turbulence, magnetic field, feedback, thermal pressure, etc., etc. In order to describe that, we need couple chemistry with magnetohydrodynamics and radiation and feedback. That's challenging. So we need to consistently treat all these processes. Maybe in some regions we can restrict ourselves to fewer processes, but I think this needs to be justified. That is sometimes difficult, and sometimes we are stretching ourselves too much. In addition, there are feedback loops. I have shown you one particular one, but there are many more on galactic scale, supernova, outflows. The global metacycle is driven by supernova. And the primordial star formation, I think, shares much of the same complexities as we see at present days. I'm done. This was the picture from my balcony this morning. Very impressive. And I want to end by showing you another picture. That is Heidelberg. The castle is hidden here. I'm walking along the Philosopher's Way, looking down at the city. And I would like to invite you all to come to Protostars and Planets 6, which takes place in Heidelberg in July 15 to 20 in the town hall, which is just around the corner. And more information is seen at this webpage, www.pp6.org. And now I'm done. Thanks. Questions? Yes.
I'm wondering, the simulation you showed yesterday, the Orion cloud simulation.
Yes.
And also today is a massive star formation simulation. If you do a cloud with the time and the number of the star formation, what kind of cloud will you expect to see? Will you see something like the number of stars and form like a saturate or increase, or what kind
I
of
see what you mean.
you will expect to see?
We know the answer to that question from observations. So the question is, how is the distribution of star formation times in such a cloud? So I think it looks like that, right? You have a bit, and then you have a peak. And it seems that this is time, and this is, let's say, the number of stars or the mass in stars, something like that. No, it must be m dot, sorry. So it is not the cumulative plot, it is the differential plot. So while the cloud is assembling, parts of it run away and give rise to very low level of star formation. We see old stars, 10, maybe 15 mega-year-old stars in Taurus in most of the nearby star-forming regions. But then there's a burst, which lasts maybe 1 million years. maybe 2, maybe less, depending on the size of the cloud. I think that is a typical star formation event, and this is associated with the assembly phase. This is what I meant if we just say, oh, the cloud is suddenly there. We only see this peak. If we allow for the formation of this cloud that then eventually makes its little starburst, then we have such a behavior. And then probably the starburst would look very different. I mean, what I've shown you, nowhere you have suddenly 1,000 solar mass blob of gas that is completely unstructured, rotates with 10 to the minus 15 1 over seconds, has an m equals 2 perturbation. This thing will be much more structured. Initial conditions matter.
Other questions? Well,
good, then we're really done.
yes.
I'm really done. Nick, not yet.
But I think we have to. Well, it's better if you don't miss your bus, which is now in something like 20 minutes.
Yes.
I would like, on behalf of the organizers, to really warmly thank you for these very, very nice lectures. We all appreciate them. I would like to give you a very little, typical Swiss souvenir from this week. So thank you very much, Ralf.
Thank you.